All right, this is part two of our discussion about intermolecular forces. All right, we take a look at question L. Dispersion forces increase with contact area between molecules. The shape of a molecule affects its surface area and how much it comes into contact with its neighboring molecules. And the question asks us which of the following molecules has the lowest and highest boiling point. And of course, the follow-on question is why? Are those the answers? We look at these. These are three different isomers of pentane, C5H12. This is a structural isomer is just three different ways to construct a molecule, especially an organic hydrocarbon that's got 5 carbons and 12 hydrogens. And we can see we've got quite a bit of different ways to build this. These are not the only ways to build this molecule, but these are 3 different ways. In fact, if we look at this, we see the boiling points go from 309 to 301 and down to 283. And we need to understand why this occurs. Molecule A has the largest surface area because it's a long, straight chain. Therefore, when we compare that to molecule C, which has the smallest surface area because it's kind of closer to a spherical shape, the increase in the surface area of molecule A drives a larger polarizability, and that increases the London dispersion forces, which cause the boiling point to be higher. All right, we move to question M. They're talking about dipole-dipole forces occurring in polar molecules, and we need to draw the structural formula of 2 trichloromethane molecules. We need to label the positive and negative ends of each molecule and use a dashed line to show the dipole-dipole force between these 2 molecules. All right, we draw the first molecule. We see the difference in electronegativity, and we draw the little red arrow with a little cross at the opposite end, pointing to the atom that's got the higher electronegativity, which in our case would be carbon. That's for the hydrogen-carbon bond. But for the 3 chlorine molecules, the dipole points in the other direction, in the direction towards the chlorine because it is more electronegative. All right, so if we do that, we can kind of see that we've got this area of negativeness or negativity on the upper right and bottom portion, which, since the whole molecule in its entirety is not charged, it's not an ion, that must mean that that left side of the molecule is a bit on the positive side to counter the negative charge on the right-hand side of the molecule. So when I draw both of these 2 molecules together, I can see that the negative side of the molecule, the gray region on the left, is attracted to the positive side of the one on the right. Okay? So this is a dipole-dipole attraction. These are not induced dipoles. These are permanent dipoles that exist in this molecule, and the positive side of one is attracted to the negative side of the other. Letter N, we need to identify which of the substances shown below has the higher boiling point and justify our answer based on structural features which drive the IMFs. Here's our 2 molecules. Very similar in weight. The one on the left has a boiling point of 355 Kelvin. The one on the right, markedly different at 231 Kelvin. The one on the left has got both LDF and dipole-dipole interactions because we can see that there clearly would be a dipole in this molecule. The one on the right is only going to be LDF. Every molecule has some sort of LDF forces. They may not be very strong, but they are present. The one on the right, because the dipoles are they're symmetric, they cancel each other out, the entire molecule is nonpolar, whereas the one on the left is very asymmetric and polar, which gives rise to dipole-dipole interactions, which means the intermolecular forces are higher, which means the boiling point is higher. These are the kind of arguments that we need to make, or to be able to make, when we're comparing substances. So this means that the CH3CN experiences London dispersion forces and dipole-dipole, but the one on the right, the propane, only experiences LDF. And dipole-dipole forces are stronger than the LDF, so the molecule on the left has the higher boiling point. Subpart O, explain the boiling point trend in the group 4A or group 14 hydrides. We see the picture of it there. Now all four of these molecules are nonpolar because they have a symmetrical shape, and since they're symmetrical, the dipoles cancel out, and all of them experience London dispersion forces, but the boiling points increase because the larger molecules have electron clouds that are further away from the nucleus, and so they are more polarizable. Therefore, they have stronger LDFs, and therefore they have a higher boiling point. Now, the follow-on question to this is, which three hydride molecules in the graph have unusually high boiling points compared to the others that are in the same series, and why? And we can clearly see that the three that have the abnormal boiling points are water, hydrogen fluoride, and ammonia. All right, so when we look at this, because these molecules experience hydrogen bonding that the others in these series don't have, and the reason that they have hydrogen bonding is because HO, HN, and HF are the target molecules that would experience hydrogen bonding. This is a very strong attraction, and that strong attraction requires energy to overcome, and therefore you have a very high boiling point considering the molecular weight. These very much do not lie in a straight line with the others. All right, question Q asks us to draw two ammonia molecules, and using a dashed line, we want to draw a hydrogen bond between them. And we need to make sure we know the difference between a hydrogen bond and a covalent bond, and it refers us to figure 1110, which is right here. All right? So the covalent bond is, of course, between the nitrogen and the hydrogen inside a molecule of ammonia. Whereas the hydrogen bond, which isn't really a bond, it's just more of a strong attractive force, which can be broken with quite a bit less energy. This is the attractive force between one molecule and the hydrogen of another molecule. Okay, so over on the drawing on the right, we see these red dashed lines. They are not bonds, but they are strong attractive forces. And they're because we use the name hydrogen bond, but there isn't really an actual bond. It's sort of a poor choice of words, but we've had it for so long, we continue to use it. All right, problem R. Ask us to circle the molecules below that are able to participate in hydrogen bonding. All right, hydrogen bonding, again, requires the attraction between hydrogen and a polar bond with oxygen, with nitrogen, or with fluorine, and a non-bonding pair in a nearby atom. And when we look at these 5 molecules, only hydrogen peroxide and hydrazine meet those requirements. So the middle one is hydrogen peroxide, and the one on the far right is hydrazine, N2H4, because these are the only ones that have hydrogen directly bonded to an oxygen, a nitrogen, or a fluorine. Question S. How does hydrogen bonding explain why water expands when it freezes? Well, that's because the hydrogen bonds in solid ice are optimized between 4 neighboring molecules to lower the overall energy. And when it does this, this creates cavities or really open spaces in the solid. And when that happens, the density goes down because the volume goes up. You still have hydrogen bonding in liquid water. It's random, but it's strong enough to hold the molecules together. Question T says an ion dipole force exists between an ion and a polar molecule like water. Label each ion below with its charge. All right, so here we've got water surrounding various ions, and you can see we have it oriented in a particular way. Now, when it surrounds a simple ionic molecule like sodium chloride, the positive end of water, the polar water molecule, aligns itself towards the negative chloride ion, and the opposite is also true. The negative side of the water molecule aligns itself to the positive sodium ion. So we can draw in a little chloride ion on the left and a sodium ion on the right to show how these ion dipole forces exist. All right, question U says all atoms and molecules experience a London dispersion force. Only the polar molecules experience the dipole-dipole forces, and only a molecule that has a hydrogen directly bonded to a nitrogen, an oxygen, or a fluorine will experience hydrogen bonding. So if an ionic substance is dissolved in a polar solvent, then you can be sure that you've got ion dipole forces that are present. Now, here comes an interesting question. We need to match the following 6 substances with their boiling point and justify your answer. And we have the 6 boiling points listed and the 6 molecules. So when we attack this, probably the best way to do this is to look at the extremes and get those taken care of, and then work our way towards the middle. Ionic bonds are much, much stronger than any intermolecular force. So that must mean that the highest boiling point has to be the ionic compound, which is calcium oxide. So that one's going to have 2850. All right, nonpolar hydrocarbons have LDF only. And when we have small size and mass, that means less polarizability, which means less LDF, which means less boiling point. So that means that the smallest of these nonpolar molecules, which on our list would be methane, would have the lowest boiling point, and propane, which is only slightly larger, will have a slightly higher boiling point. So now we've knocked out 3 of those 6. Now, next we know that dipole-dipole forces are stronger than LDF. Now, when we look at this next one, we see that fluoropropane is polar, but it doesn't have hydrogen bonding because the fluorine is attached to a carbon. So that's going to be the next one up at -3. And that leaves us both of the remaining molecules which have hydrogen bonding, but the diol, the 1,3-propane diol on the right side, has twice as many hydrogen bonds in the molecule. So it's going to have the highest boiling point because there's just more opportunities for more attractive forces. So we assign the higher temperature 211 to the propane diol, and the lower of the 2 remaining temperatures, 98, to the propanol. All right, that's where we're going to stop for this video. We'll pick up in the next one.